This is the review for our first exam, and I'm going to go over some problems, but I'm not going to go over all of them. I think there's some of these things that you should be able to look up in your textbook, like the definition of function, definition of function being one-to-one, and so you should also be able to come up with examples of things that are functions and not functions, and examples of things that are one-to-one and not one-to-one. So let's skip over this problem and go on to number 2. Number 2 is all about lines. It says here to find an equation of a line with a slope m is equal to -2 passing through the point 5, -5. So this is nothing but a formula. Y minus y1 is equal to m times x minus x1. And if you solve for this, you have your y, your y1 and your x1. That's y1 is -5, x1 is 5, and then your m is 2. So let's just plug that into the formula. Y minus y1 is equal to the slope, -2, x minus x1. And I would be happy with this answer right here. If you leave it at that, that's good. Some people prefer to write it in the y equals mx plus b form. You can go ahead and do that if you want. Number 2, determine if the lines 2x plus 3y equals 1 and 3x plus 2y are parallel, or is equal to 5 or parallel. So to figure out whether something is parallel or perpendicular, it all depends on the slope. And to find the slope, you need to get y by itself to write it to the y equals mx plus b form. So let's work with this equation right here. Let's take 2 to the other side. 3y is equal to -2x plus 1. And I like to get the x here so it looks like the y equals mx plus b form when I divide through. So y is equal to -2/3 x plus 1/3. So when you divide by 3, it has to distribute to those. And here your slope is -2/3. So let's check the slope of the second line. Looks like we need to do the same business. We got 2y is equal to -3x plus 5, and then divide by 2. Y is equal to -3/2 x plus 5/2. And now we look at the slope for that. Now the slopes are not the same. Because they're not the same, they're not parallel. If they're perpendicular, we should be able to multiply them. So the slope for the first one is -2/3. The slope for the second one is -3/2. And we're seeing that these things cancel and becomes +1. Now if the answer was -1, then they would be perpendicular. But m1, m2 being multiplied equals -1 means the lines are perpendicular. It's not equal to -1, it's equal to +1, so it's not perpendicular, and it's not parallel, so it must be neither perpendicular nor parallel. Okay? Part C, find an equation of a line passing through the point and parallel to the line y is equal to -5x minus 8 plus 7. So if it's parallel to this line, we need to have the slope to be the same. So what is the slope of this line? Well, we can find the slope. The slope is actually -5 if you want to just multiply things out just to be absolutely sure. You get -5x. This is +40 plus 7. So now it looks like it's in y equals mx plus b form, and then you can clearly see that -5 is the slope. So going with this slope and this point, we just use the same equation that we did in the first problem. Y minus y1, that's -8, is equal to -5, that's m. X minus x1, and x1 is -9. So again, I'd be happy with this answer, or you can write it into y equals mx plus b if you want. Let's be done with that one. Part D, It says a phone company charges $7 flat fee plus 5 cents. This actually should say 5 cents. This was a typo. 5 cents per minute. Write an expression that would give the total amount charged in a month where you were on the phone for 100 minutes. So let's first write your flat fee, $7, plus a 5 cents per minute charge. So 5 cents, 0.05 per minute. So this is the cost for your bill. So this is your expression, and what happens if you had 100 minutes? So C of 100, this is putting in 100 in for M, so that's $7 plus 5 cents times 100 minutes. So 100 minutes, let's move this thing twice, decimal point twice to the right, and then that would be 5. So this is $7 plus $5. And it looks like it's going to be $12 for that month. Okay, so that's problem number 2, all about lines. Problem number 3 is asking us to sketch the graphs and identify asymptotes and label some points on the graph. Alright, let's see if we can do this neatly. This one is an exponential function, and it's an exponential function where the base is less than 1. So y equals b to the x. There's 2 graphs. It either would be going up or going down, depending what b is. Here, this is b bigger than 1, and here it would be an exponential decay, b less than 0 or less than 1. So we have a case where b is less than 1. So our graph would look like this. It's asking us to label a point, and so the best point to label, the easiest point to label here, is when x is equal to 0, y is equal to 1. So let's say 0, 1 for that point. Okay, that's the first one. Let's choose another color for the second one. Let's label this graph too, since we're going to have a messy page here. Y is equal to 0.08 to the x power. Alright, the second one, y is equal to log base 7 of x. So the log function generally would look like this for any base, and depending on your base, it'll match up some certain shape and be closer to the x-axis or further away from the x-axis. But we can definitely label this 1, 0, and this is y equals log base 7 of x. And if we really wanted to, we can label one more. I think if we hit 7 over here, we're going to get a y value of 1. So this is 7, 1 would be another point. Okay, now let's squeeze in the cosine function. Oops, let's use a different color for that. So the cosine function starts off at 1, and the sine starts at 0 and oscillates. This starts off 1, this finishes one whole period at 2 pi. So this would be good enough to show, but you can keep going forever if you want on both sides. And label a point, 0, 1 would be a good point. Another good point to label would be 2 pi, 1. Then you can label a bunch more points if you want, but this is the cosine function. Okay. Alright, now let's do this side. We got x to the 6. X to the 6, generally the power functions kind of look like this in general. For even powers, they would go up on the left side for odd power, so they would go down on the right side. So 0, 0 would be a good label, and 1, 1 would be another good label. But that looks awful lot like a bunch of other power functions. X to the 6. So if you want, you can put a 2 and then whatever 2 to the 6th is. 64 maybe, something like that. Anyways, I'll just label 1 and 2. And actually, I don't know if you guys have compared more power functions, but the higher the power is, the closer this is going to be to the x-axis. The flatter the u is going to be. Alright. Let's do the next one, the cube root function. So square roots and cube roots kind of look like sideways parabolas. So this is y is equal to the square root or cube root of x. Now the difference is the square roots and anything with an even root stops. But if you have an odd root, since you can have a negative under a square root, this is defined, so it continues on. So this is again 0, 0, and one more point if we wanted to is 1, 1. An interesting comparison between graphs is that if we were to graph the x cubed function and the cube root function, they would be inverses of each other, and they would be reflected about the y equals x line. And finally, we have the absolute value, and the absolute value looks like this. So this is y is equal to absolute value of x. Crosses here at 0, 0. Also crosses at 1, 1. Then you can label a bunch of other points if you want. One of the things that we did discuss in class was that the fact that this absolute value is not differentiable at 0 because of the corner. And so that's just something to look at sometime. So that's problem number 3. Moving on to problem number 4, we have the graph of f of x is given on the same axis. Plot the following. We have f of x plus 2. So this looks like it's a shift. Now if we draw the exact same graph over here, it's a little bit off, but let's see. And a shift, this is a shift to the left by 2 units. So let's take this, oops. I wanted to take, let's try that again. I wanted to take the blue graph and shift it 1, 2 units. So that's how it would look like, shifted 2 units. So all you're doing is you're essentially copying this thing, shifted 2 units. Alright, the next one, we have 0.05x. Now this thing is a stretch or compression vertically, and because it's less than 1, it actually will stretch it by a factor of 0.5. So basically by a factor, it'll compress it by a factor of 0.5 or stretch it by a factor of 2. So what used to be, well, what's at 0 is going to stay at 0, and instead of going to 1, it's going to get doubled by a factor of 2, and same thing over here. Now this point over here that used to be at 2 is going to get stretched to 4, and this point over here that used to be at -2 is going to get stretched to -4. So let's see if we can draw that out. So this is that curve that used to be like a little half of a circle, and this thing is a straight line. I got stretch, and this thing continues down here. So it basically stretches your graph upward from the y-axis. Alright, the next one, negative x. Negative x is some sort of reflection. The negative on the inside is a reflection about the y-axis. So let's see, this stays, anything in the y-axis will stay the same. This will stay the same, but now instead of going up here, it'll go up there, and it'll go down here. So this is how this graph would look like, a reflection. Alright, and the last one, give a function that would take f of x and reflects it across the y-axis and stretches it vertically by a factor of 3. So reflect about the y-axis, that's kind of like similar to this, and then stretch it vertically by a factor of 3. So we don't need to draw the picture, but if you were to draw the picture, when your function originally looks like this, stretching it or reflecting it across the y-axis would look like this, and then stretch it by a factor of 3 would stretch these things to 3, and then if it's at 0, it stays at 0. So it gets stretched out by a factor of 3, and this thing goes by a factor of 3 up as well. So your final answer, if you were to graph this, would be in red, but the actual function would look like this. So we got a reflection about the y-axis, so f of negative x, and then we got a vertical stretch by a factor of 3. So that's how that would look like. Alright, so these are transformations of functions. Number 5, we have the arcsine function. It's asking us what the domain and range are for this function. So let's take a look at the arcsine function. Remember the sine function, maybe we can start with that. The sine function looks like this, and remember that it goes on forever, so we're interested in finding a restriction so that it would be 1-to-1. So that's this part, and then what we're going to do is we're going to reflect that. So let's figure out the restricted domain first. We're just going to go negative pi over 2 to pi over 2, and we're including that while our current range goes from -1 to 1. So now if you imagine flipping that over, this is your sine function, by the way, and your arcsine function then would look like this. So what used to be the domain of negative pi over 2 to pi over 2 is now a range of negative pi over 2 to pi over 2. And what used to be the range from -1 to 1 is now the domain from -1 to +1. So this is your arcsine function. So let's mention the domain is all the set of x values from -1 to 1. Let's just use the interval notation, -1 to 1, and we're including -1 to 1. The range, including negative pi over 2 to pi over 2. And then this is a graph. Draw at least 3 important points. We got this important point 0, 0. We got this important point 1, comma pi over 2. And another important point -1, comma negative pi over 2. Okay. It says to simplify the arctan of the sine of x. Let's see. Or the tangent of the arcsine of x. So tangent of the arcsine of x. So what we have to know is that the arcsine of x is a y value. You can think of it as a y value, or you can think about it as an angle if you want. So let's see, this is going to be a little tricky. what we want to do is think about let theta equal arc sine of x, and so because of the inverse properties we can say the sine, we can think about taking the sine to both sides. X is equal to sine theta. Now I think if we use some trig we can use or take advantage of our triangle, and this is the theta that we're looking for, and the sine is the opposite value over the hypotenuse value, so this is x over 1, and then so I think it would be important for us to figure out what this adjacent side is. So let's figure that out. Using Pythagorean's theorem, if we call this adjacent side, I don't know, y, let's not call it y, let's call it b. Then we have x squared plus b squared is equal to 1. So, and sticking with a positive side, we can say b is equal to 1 minus x squared, bringing the x squared to the other side. Now taking the square root, let's just consider the positive side, and so we have b is equal to square root of 1 minus x. So that's what this is, square root of 1 minus x. Now if we redraw that triangle, you don't need to, but I'll redraw it anyways. And this is theta, this is 1, and we're looking for the tangent of theta. Using this triangle, the tangent is the opposite of the hypotenuse, or opposite over the adjacent. So the tangent is going to be the opposite side over the adjacent side. So that's x over the square root of 1 minus x squared. Alright, so that is our last problem for number 5. Number 6 brings us to some theory questions. And then here are some theory questions. I don't think I'll be testing you on this much theory stuff, but let's just take a quick look and so you can see some more examples of things. If a function, then f of a b is equal to f of a plus f of b. This is false, and usually when things are false it's always good to think about a counterexample, and the easiest counterexample would be let's say f of x is equal to x squared. Then f of, let's put 1 and 2 here, f of 1 plus 2 is equal to, is this equal to f of 1 plus f of 2? Well, the square says we take whatever's in the parentheses and we square it, and 1 plus 2 is 3 squared, and that's equal to 9. Let's see if this will follow. 1, f of 1 is 1 squared, f of 2 is 2 squared, and then 1 plus 4, that's equal to 5, and so this is not equal. So this is a counterexample, and that's why that's false. Second one, f and g are continuous, then f of g is the same as g of f. This is the composition. So again, we can use simple functions like this, and then I can use another one. So let's say I'll use the same f over here. F of x is equal to x squared, and maybe let's say g of x is equal to x plus 1. So f of g, so f of g is the same thing as f, and then g goes inside x plus 1, which is, this says when you take whatever's inside here and you square it, this is x plus 1 squared. Whereas g composed with f is g, and then inside is f, that's x squared, and g is x plus 1, so whatever's inside here gets replaced by x, so that's x squared plus 1. You got to convince yourself that these two things are not equal, because if I were to multiply this out, the first one, x squared plus 2x plus 1, and this one does not have that 2x there, so these two are not equal. So that's why this is also false. The rest of them I'll go by real quick. F is 1 to 1, then the inverse is equal to 1 over x. This is false. Remember that the trig inverses are not the reciprocal. The inverse sine, for example, is not equal to cosecant. So that's false. If a is less than b, and a is positive, then ln a is less than ln b. So I'll say this is true. I won't prove it. I'll just say it's true. X is any real number, then the square root of x squared is equal to x. This is true also. Actually, no, it's false. Because I would ask you to try, what if you put a negative 1 in there? This is going to be a positive on one side and negative 1 on the other side, so that's not true. And here f is decreasing, then f of a, if a is less than b, then f of a is greater than f of b. This one is true. This is the actual definition of decreasing functions. So I think those examples are just important for us to take a look at, and if you can understand them, great. If not, then it's not something to worry too much about for the test. It's all kind of pre-algebra, or I'm sorry, pre-calculus review. Alright, let's go to our last problem for this first part of the exam. And here we're asked to simplify the difference quotient, where this is your function. Alright, now remember how to use this function notation. It's replacing this whole expression in for x wherever you see an x. So the first one is putting an a plus h wherever you see an x. So what might be a good start is to say that this whole thing is f of a plus h. Wherever I see an x, I'm going to replace it with an a plus h. And then we have a minus, and then you have the f of x, except instead of using x, you're going to replace it with a. So I usually like to write my functions with these function holder parentheses. And again, wherever I see an x for this, I'll replace it with an a. So that's the whole numerator. The denominator is just h. Alright, so let's see how this is going to work out. Let's FOIL this out. This is going to be a squared plus 2ah plus h squared. Let's distribute the 6, minus 6a minus 6h. That's distributing a negative 6. We have a 5, and then we have a minus. This is just a squared. Minus and minus becomes a plus 6a, and a minus and a 5. Divide that whole thing by h. Now I'm going to take a quick look at this and notice that there's an a squared and an a squared. One's positive, one's negative, so that's gone. There's a 6a here that's negative, a 6a here that's positive. They're both gone. And then a positive 5 and a negative 5, so that's all gone. So what we have left here is a 2ah plus h squared minus 6h divided by h. And now if we factor out an h from the top, we get a 2a plus h minus 6 all over h, and then the h's will cancel. And so we have our final answer is a 2a plus h minus 6. Okay, so that's the difference quotient, and all this stuff is all, like I said, pre-calculus and a little bit of a review. If you don't remember it, there's some of these things that aren't that important, but we're going to touch on them a little bit later on in the course. Okay, so we'll take a break and we'll come back and do the second part of this review.